Imagine an earthquake so powerful it shakes not just a planet but an entire star. This is not science fiction. It is a real event, a cosmic spectacle of unimaginable force. These are called starquakes. They happen on the most extreme objects we know of in the universe. Neutron stars. When one of these stars cracks, it releases more energy in a fraction of a second than our sun will produce in thousands of years. It is a moment of pure, raw power, a testament to the violent and beautiful physics that governs our cosmos. This is the story of what happens when a star breaks. Think about the most violent event you can picture on Earth. A volcanic eruption, perhaps, or a massive earthquake shifting continents. Now, try to scale that up. Not just to the size of a planet, but to the size of an object that contains the mass of our sun, crushed into a sphere no bigger than a city. The forces at play are almost beyond human comprehension. When the solid crust of such an object gives way under immense strain, the resulting tremor is a cataclysm that sends ripples across the galaxy. It is a cosmic shudder. To understand a starquake, we must first understand the stage upon which this drama unfolds, the neutron star. A neutron star is the leftover core of a massive star that has died in a spectacular explosion called a supernova. After the star's outer layers are blasted away into space, the core collapses under its own immense gravity. It collapses so much that all the empty space within its atoms is squeezed out of existence. Protons and electrons are forced together to become neutrons, creating an object made almost entirely of these subatomic particles packed side by side. The result of this collapse is an object of truly staggering density. Imagine taking our sun, a star so large that over 1 million Earths could fit inside it, and crushing it down. Imagine it shrinking until it is only about 20 kilometers across, the size of a city like Manchester or London. A single teaspoon of its material would weigh billions of tons here on Earth, as much as a mountain. This incredible density creates a gravitational field that is second only to that of a black hole. It is a place where the fabric of space-time itself is warped and twisted into extreme shapes. This extreme nature gives neutron stars some very peculiar properties. Because they are formed from the collapsing core of a much larger spinning star, they spin incredibly fast. Just as an ice skater spins faster when they pull their arms in, a neutron star's rotation speeds up dramatically as it shrinks. Some can rotate hundreds of times every single second, faster than the blades of a kitchen blender. This rapid spin, combined with their powerful magnetic fields, can cause them to sweep beams of radiation across the cosmos, like a cosmic lighthouse. When these beams sweep past Earth, we see them as regular pulses of radio waves. When they were first discovered in 1967, the regularity of these pulses was so precise that astronomers briefly considered the possibility that they were signals from an alien civilization. We now know that they are the natural ticking of a cosmic clock, the steady beat of a rapidly spinning star. But it is the structure of these stars that is key to understanding starquakes. They are thought to have a solid outer crust, a bit like the crust of the Earth, but made of iron and other heavy elements arranged in a crystal lattice. This crust is incredibly strong, perhaps the strongest material in the universe. But beneath it lies a sea of superfluid neutrons and other exotic particles under unimaginable pressure. A starquake is in essence exactly what it sounds like, a quake on a star. It is the neutron star equivalent of an earthquake. On Earth, earthquakes happen when tectonic plates in our planet's crust shift and grind against each other, releasing built-up stress. On a neutron star, something similar happens, but on a scale that is almost impossible to grasp. The star's incredibly rigid crust is put under enormous strain by the intense forces churning within and around it. Eventually, the stress becomes too much for even the strongest material in the universe to handle, and the crust fractures. This fracturing is not a gentle process. It is a sudden, catastrophic failure. The crust cracks and rearranges itself in a violent convulsion. This movement might only be a few centimeters, but on an object as dense and massive as a neutron star, that is enough to release a colossal amount of energy. The star's surface rings like a bell that has been struck by a cosmic hammer, sending powerful vibrations through its interior. This sudden release of energy is what we observe as a starquake, a brief but incredibly luminous burst of radiation that outshines entire galaxies for a moment. These vibrations are the star's response to the sudden, violent rearrangement of its crust, a cosmic tremor of unimaginable power. These seismic waves are not like the gentle ripples in a pond. They are waves of pure physical force traveling through the densest matter known to exist. While starquakes can happen on any old neutron star, the most spectacular and violent events are reserved for a very special class of object, the magnetar. These are the true monsters of the stellar graveyard, the undisputed champions of cosmic extremism. A magnetar is a type of neutron star, but one that possesses a magnetic field of truly unimaginable power. While a typical neutron star's magnetic field is already trillions of times stronger than Earth's, a magnetar's field is up to 1,000 times stronger still. This makes it the most magnetic object known to exist in the entire universe, a cosmic lodestone of terrifying intensity. The forces at play are simply mind-boggling. This colossal magnetic field is not just some invisible force. It is a dominant feature that shapes the magnetar's entire existence and environment. It is so powerful that it can physically distort the star itself, squeezing it into a slightly oblong shape and putting immense constant stress on its solid crust. The energy stored within this magnetic field is immense, far exceeding the energy of the star's rotation. The origin of these ultra-powerful fields is still a topic of intense scientific debate. One leading theory suggests that if a newly born neutron star is spinning exceptionally fast, perhaps completing a rotation in just a few milliseconds, it can create a powerful dynamo effect. Living near a magnetar would be impossible. Its magnetic field is so strong that it would be lethal from over 1,000 kilometers away, tearing apart the atoms in your body. Even from the distance of the moon, it would wipe the data from every credit card on Earth. This is the stage upon which the most powerful starquakes, or superquakes, unfold. The immense magnetic energy stored in and around the star provides a vast reservoir of fuel for explosions. On December 27, 2004, humanity witnessed the power of a magnetar superquake firsthand. A giant flare erupted from a magnetar known as SGR 1806-20, located about 50,000 light-years away on the other side of our Milky Way galaxy. In the first tenth of a second, the burst released more energy than our sun has emitted in the last 150,000 years. It was so powerful that even from this immense distance, it saturated the detectors of every gamma-ray satellite in orbit and was bright enough to physically disturb Earth's ionosphere, the upper layer of our atmosphere. It was, honestly, a cosmic shot across the bow, a stark reminder of the power lurking in the cosmos. The initial spike of the flare was followed by a long, pulsating tail that lasted for several minutes. As the magnetar spun, the hot spot created by the explosion swept past our line of sight, creating a rhythmic pulse in the X-ray signal that perfectly matched the star's 7.6-second rotation period. This allowed astronomers to confirm beyond any doubt that the source was a magnetar. The sheer brightness of the event was historic. If the flare had occurred within just 10 light-years of Earth, it would have likely triggered a mass extinction event, stripping away our ozone layer and bathing the surface in lethal radiation. Studying the aftermath of this giant flare provided unprecedented insights into the physics of magnetars. The 2004 event remains the most powerful starquake ever recorded and serves as the benchmark for understanding these extreme phenomena. Starquakes are more than just distant, violent spectacles. They are invaluable tools for science, cosmic laboratories where we can test the limits of our physical laws. Here on Earth, we can never hope to replicate the conditions found inside a neutron star. The pressures are just too high, the gravity too strong, and the densities too immense for any experiment we could build. But, nature has provided these laboratories for us, scattered all across the galaxy. When a starquake happens, it sends us a postcard from this impossible realm. The light from the quake and its afterglow carries precious information about the physics of the ultra-dense, a message we can decode from the safety of our own world. By studying the light from a starquake, especially those high-frequency flickers in its X-ray afterglow known as QPOs, astronomers can perform asteroseismology. This is basically the science of studying a star's interior by observing its vibrations, much like a geologist studies earthquakes to learn about the Earth's core. These oscillations are the direct signature of seismic waves ringing through the star's crust and core. The specific frequencies of these vibrations depend entirely on the properties of the material they are traveling through. It is, honestly, a remarkable way to map the inside of an object we will never visit. These events also provide a perfect testing ground for Albert Einstein's theory of general relativity. Neutron stars are objects where gravity is pushed to its most extreme, second only to black holes. The gravitational field is so strong that it profoundly warps the fabric of space-time around it. A starquake, with its sudden release of energy and mass redistribution, causes ripples in this space-time fabric. While we cannot yet detect these gravitational waves from individual starquakes, studying the light that travels through this warped space-time allows us to test Einstein's predictions with incredible precision. Perhaps the most profound mystery that starquakes help us explore is the fundamental nature of matter itself. Deep within the core of a neutron star, matter is crushed to a density so high that, honestly, our current theories begin to break down. We simply do not know for sure what it is made of. Physicists have many competing theories, each describing a different exotic state of matter. Is the core just a simple sea of tightly packed neutrons? Or does the immense pressure crush the neutrons themselves, liberating their inner components, quarks and gluons, to form a new state of matter called a quark-gluon plasma? Starquakes offer one of our best hopes for an answer. The key lies in how the star vibrates. The different proposed states of matter for the core, be it a neutron superfluid or a quark soup, would behave very differently. They would have different levels of squishiness and would transmit seismic waves at different speeds. Therefore, a star with a solid quark core would ring differently than one with a fluid neutron core, just as a bell made of brass sounds different from one made of steel. By carefully measuring the frequencies of the seismic waves, those QPOs from a starquake, scientists can compare the data to their models. They can effectively listen to the star's vibrations to determine what its core is made of. This quest is about more than just understanding weird, distant stars. It is a search for the ultimate equation of state for cold, dense matter. This equation of state is a fundamental rule in physics that describes how matter behaves under any given pressure and temperature. Finding it would be a landmark achievement, completing our understanding of the building blocks of the universe. Starquakes, by probing the densest stable matter that can exist, provide crucial data points for this equation. They are cosmic experiments that help us piece together the puzzle of how matter works at its most fundamental level, a puzzle that began with the Big Bang itself. In essence, every starquake that we detect is a gift. It is a fleeting glimpse into a world that is otherwise completely inaccessible. It allows us to test our most fundamental theories of gravity, magnetism, and matter in a regime that we can never reproduce. For all that we have learned from starquakes, they continue to hold deep and profound mysteries. We have peered into their violent hearts, but many of the most fundamental questions remain unanswered, driving the next generation of astronomical research. Perhaps the greatest puzzle of all lies deep within the neutron star's core. What is it truly made of? Do neutrons remain as neutrons, or do they dissolve into a primordial soup of quarks and gluons? Another significant mystery surrounds the magnetars themselves. We believe their colossal magnetic fields are the key to their giant flares. But how are these fields generated in the first place? These unanswered questions are what make the study of starquakes so exciting. Every new observation has the potential to unlock a piece of the puzzle or to reveal an entirely new mystery. Are there other, even more exotic phenomena associated with them that we haven't yet detected, such as powerful bursts of gravitational waves? Could they explain other cosmic mysteries, like some of the fast radio bursts we see from distant galaxies? The broken stars of the cosmos still hold many secrets. As we continue to listen to their cosmic echoes, we are not just studying the death of stars, but probing the very heart of matter and the fundamental laws that govern us all. Our cosmic journey has taken us to the very edge of physics, to the surface of the universe's densest objects, and into the heart of its most violent tremors. Starquakes represent a perfect storm of celestial extremes, combining unimaginable density, mind-bending gravity, and the most powerful magnetic fields known to exist. Their enduring fascination for astronomers, and for all of us, lies in this very extremism. They are a stark and beautiful reminder that the universe is not a quiet, serene place. It is dynamic, often violent, and filled with phenomena that push the boundaries of our comprehension. Ultimately, starquakes connect us to the grand life cycle of the cosmos. They occur on the stellar corpses left behind by massive stars, the very same stars that created the heavy elements in their cores that are now part of our planet and our bodies. The light from these events travels for thousands of years across the galaxy, carrying the secrets of the star's broken crust and vibrating heart. By catching these faint echoes, we are not just witnessing a distant catastrophe. We are using the universe as its own laboratory to answer some of the deepest questions about its own construction.